Right, question 7, closed system. So a closed system just means nothing can basically get in or out. Right, so nothing can enter or leave the system, i.e. like a closed beaker. Explain why when a reversible reaction reaches equilibrium, the reaction appears to have stopped. So it appears, note it says appears, it hasn't stopped, it appears to have stopped. And of course that is because the forward and reverse reactions are going at the same rate. That is, of course, the whole definition of equilibrium, isn't it? So if they're going at the same rate, notice there's 2 marks here, we need a bit more than this. So what does that actually mean? Well, it means that the quantities of reactants and products are going to stay unchanged, or the concentrations are going to stay unchanged. So the concentration, or if you like, quantity of reactants and products stays unchanged, is unchanged. Right, fantastic. Okay, next part, what's going on here? Where are we? Here we go. Right, so it then says in the Haber process, right, the Haber process is a industrial process which we shall study a little bit more in the future, but in the Haber process the reaction of nitrogen and hydrogen produces ammonia and is reversible. So that stuff there is ammonia, nitrogen, hydrogen, reversible. Name a natural resource. Okay, so we haven't formally studied this, but you might be able to guess. So a natural resource which contains hydrogen. They are looking for either a hydrocarbon, such as methane, CH4, or URL, which I imagine a lot of you will have guessed at, water. If you electrolyse water, you can get hydrogen from that. Right. Explain how the catalyst speeds up the reaction. This is very familiar. It's exactly the same as last time. All right, so it will, of course, still provide an alternative pathway. And that alternative pathway, of course, has a lower activation energy, which I am writing, honestly. Right, 2 marks, brilliant. What happens to the amount of ammonia at equilibrium if the pressure is increased? Pressure, it's all about molecules. Let's have a little look. So we have 1, 2, 3, 4 on this side, 2 on that side. Increase the pressure, that goes to the side with the least. Done, easy peasy. Right, so therefore the yield increases. Why? There are less molecules on the right. Okay, so that should be pretty straightforward. Part C, let's shimmy down to that one. Oh, this one, right, okay, so we have here hydrogen iodide, hydrogen and iodine. Forward reaction is endo, so the other one is exo. There's a lovely energy level diagram. Draw an arrow to show the activation energy. Okay, will do. So that is the energy required to break the bond. So it should go from this point, you don't need to draw this line, this point all the way to the top. Don't be lazy, make sure it goes all the way to the top. And why not label it EA? Sounds like a plan. Right, so that's your activation energy done. Next bit. How does it show that it's endothermic? Okay, so if you look back over here, where's it gone? Endothermic, it's all about the relative height of the reactants and the products. Okay, so essentially all you need to write is that the reactants are at higher energy than the products. No, they're not. That's a complete lie. Let's try that again. The reactants clearly aren't at higher energy, are they? That'd be exo. So the reactants are lower in energy than the products. Reactants are lower energy than the products. Okay, so that's that one. Suggest what effect increasing the temperature would have on the amount of hydrogen iodide. Right, so increase the temperature. If you increase the temperature, it tries to do the opposite, so it tries to cool itself down, so it will go in the endothermic direction. What are we looking at? The amount of... Oh, sneaky. Right, so just be careful here, because they're actually asking about this stuff. So if you increase the temperature, it moves to the right, so the amount of HI will decrease. Okay, so just be careful about that. So it decreases. And again, reasoning-wise, all you have to do is to say that the forward reaction is endothermic. And of course, what does that mean? It means the equilibrium, which I'm going to shorten to EQM, moves to the right. Whoops. Okay, put that in brackets. Just a little note about this particular reaction. It crops up a lot. They normally, because they're all gases, they often ask about what happens when you increase the pressure. But of course, the whole point here is if you've got two molecules this side and two that side, changing the pressure will have no effect whatsoever.